power systems and energy systems to make communities more resilient to the effects of climate change. And this is important because even though we've been spending a lot of time talking about different technologies for mitigating climate change, slowing the rate of climate change, potentially even stopping climate change altogether, we kind of are pleasantly ignoring this simple fact that the climate has already changed, irreversibly and irrevocably. And in this post-climate change world, we have to start developing technologies not only for mitigation, but for adaptation to this new environment. And in particular, one of these effects that I focus on is more frequent and more devastating natural disasters that arise from the oceans and the climate becoming more and more warm. And these big storms, in particular hurricanes that I'm going to be talking about here, have the potential to leave millions of people without potable water and electricity in their aftermath. And currently, disaster relief is super expensive and not the most effective process currently. If we use Puerto Rico after Hurricane Maria in 2017 as a case study, it was reported that 10 million water bottles were lost during the initial aid efforts after the storm, despite the fact that thousands of people were without water, fresh water, for a month or so after the storm. And it's actually just reported that these water bottles, over a year later, a couple months ago, were just disposed of. 75% of Puerto Ricans were without power for a month after the storm. This was due to 80% of power lines in Puerto Rico being downed and the lack of infrastructure to bring backup generators out to the people who need them, in particular in remote communities. And then there's this third problem that natural disasters have, and that's they produce an incredible amount of debris. But what people don't realize is that a lot of this debris is actually incredibly energy dense. In particular, aluminum has an energy density of 23 kilowatt hours per liter. That's 40 times the energy density of lithium-ion batteries. And after a natural disaster like a hurricane, aluminum debris is incredibly abundant because of damaged cars and homes which use aluminum as construction materials. And so my goal here explicitly is to figure out ways of extracting that energy from aluminum debris to enable access to clean water and electricity to power critical pieces of equipment that people need during initial aid efforts, and in general just to make communities more resilient to these effects of climate change that can remove your access to clean water and electricity in an instant. And so we can actually do this already. We can take aluminum debris, we can convert that into a water-reactive aluminum fuel. We can then react that aluminum fuel with water to produce hydrogen, which can be used to generate electricity. And then this aluminum water reaction is highly exothermic, so we can use that heat that's released to provide fresh water via seawater desalination. And before I get into the details of this process, I'd like to take a step back and talk a little bit about why aluminum is a good fuel and where it doesn't make sense to use it as a fuel. And so, as is shown here by this plot of volumetric energy density by gravimetric energy density, we see that aluminum is way up here. So that means it can pack a lot of energy into a small volume. In fact, it can pack twice the energy for the same volume as diesel and gasoline, and about 40 times, as I mentioned, lithium-ion batteries. But aluminum currently might not make the most sense as a primary fuel source. So if I were to tell you that aluminum is the third most abundant element on Earth, and that it has the energy density that it does, you'd say, why aren't we using aluminum to power everything then? And it's the simple fact that aluminum, despite being the third most abundant element, is most commonly found in bauxite ore. And it's most commonly found fully oxidized as aluminum oxide or even aluminum hydroxide. And it actually requires about 41 kilowatt hours per liter of aluminum to strip those oxygens off that aluminum. And if you remember my 23 kilowatt hours per liter figure, that's about twice the energy that it gives us back. So that might not make the most sense. And the other issue that compounds this is that the current process most commonly used for removing that oxygen is an electrolysis process that uses a graphite anode to essentially pull those oxygens off, combine them with carbon, and then release carbon dioxide. So this is not a green process either. And people are developing inert anodes for this process, but they're not at full-scale production yet. And I think we are definitely moving in the direction where we could use aluminum as a primary fuel, but we're not there yet. And that's not what I'm advocating here that we do. So the other thing to do then is to look at other places where aluminum is abundant and where we can actually extract this energy at pretty minimal impact to the environment. And that's after these natural disasters, and especially in these small island developing states, where a lot of this aluminum debris ends up in scrapyards and landfills. And so if this aluminum is just ending up in the trash, that's a lot of energy that we're not recapturing. And so if we can take this aluminum, convert that into a fuel, and extract that energy, then we can improve the efficiency of the entire process. And we're not taking that hit of the carbon emissions from that primary aluminum production. And I should mention here that in places like Puerto Rico and the Dominican Republic, which are highly susceptible to these natural disasters, aluminum is about 50 cents a kilogram for scrap. And so, of course, there's no free lunch here either. You would take aluminum as in some arbitrary geometry, and you'd probably want to break that down into smaller pieces. And so just a quick back-of-the-envelope calculation to determine how much energy is required to shred and then compact aluminum into uniform pellets. That's only about half a kilowatt hour per liter. So again, compared to that 23 kilowatt hours per liter that I mentioned earlier is embodied in that aluminum, this is pretty much negligible. So how do we take those pellets and turn that into a fuel? Well, we use here at MIT a process that was developed in-house a couple years ago, where we take that pelletized scrap aluminum, we treat the surface with a small amount of gallium and indium, and then we just let it sit out for 24 hours or so at room temperature. And ordinarily, aluminum has this oxide layer on the outside that prevents it from reacting with water. But what we've found is that using this process, here we go, the gallium and indium actually have the capability to disrupt this oxide layer at the grain boundaries where this gallium and indium eutectic sits. And you can see in this microscopic video here that hydrogen is being evolved at the grain boundaries. And in fact, this process allows the aluminum to react to over 90% completion. And so how much a gallium and indium is required? Well, we discovered that here on this plot here shows reaction yield, which is how much of the aluminum has reacted to produce hydrogen versus the mass fraction of eutectic gallium and indium in the fuel. And we've discovered that you only need about 2.5% to get to that 90% reactivity yield. And that if we increase it to about 4.5%, we're now over 95% reaction yields. And because the gallium and indium is not consumed in this hydrogen generation process, the eutectic is actually recyclable, and we can use it to make new fuel again. So now that we have this fuel, we can react it with water to produce hydrogen, and thermal energy is released in that process. And you can see the sped up video here. It'll loop around in just a second. But we add the aluminum. So let me back up, play one more time. We combine aluminum and water in some sort of vessel. You see immediately hydrogen is produced. We're producing some byproduct, which I'll talk about in a second. And you can see that the thermal energy is actually boiling off the remaining water before the rest of the aluminum can react. So it is an incredible thermal energy release as well. And there are a number of reactions that can possibly happen that combine aluminum and water to produce hydrogen and then either aluminum oxide or some other hydrated aluminum oxide. And it's important to know which one of these reactions is occurring. So recently we've figured that out. And it's basic thermodynamics where you can determine the favorability of a reaction by looking at the Gibbs free energy of that reaction. So we can plot the Gibbs free energy for the different candidate reactions. And we know that that's going to be a function of pressure and temperature. And so the lowest change in Gibbs free energy across those different reactions at a particular temperature and pressure tells us the most favorable reaction to occur at those conditions. We can then project these Gibbs free energy surfaces down onto that temperature pressure plane and plot the intersections. And that gives us a nice map of where on this pressure temperature plane the different reactions are most likely to proceed. We can simplify this a little bit further because we observed that this type of fuel, this type of aluminum activated in this manner does not react well with high temperature steam. And so above the saturation curve of water at these pressures, we've noticed limited reactivity. So we're really just left with these two regimes here. And this is, again, important because you'll notice that we have the same amount of hydrogen for aluminum that's produced here, but the amount of water changes by about 50%, and the byproduct is different. We have aluminum oxyhydroxide in this regime and aluminum hydroxide in this regime, and they have different market values actually in different places of the world. And then finally, the amount of heat that's released in this reaction also changes depending where you are in this map. And to give you an example, if we react this aluminum at atmospheric pressure at about the boiling point of water, 100 C, we find that we get 11 kilowatt hours of heat per liter of aluminum that we react. And then the lower heating value of the hydrogen that's evolved in this reaction is about 12 kilowatt hours per liter worth of aluminum. We validated this thermodynamics model recently by just reacting aluminum and water at the extremities of this temperature and pressure range, and then validated that the byproducts were what we thought they were using Fourier transform infrared spectroscopy and X-ray diffraction. And the results matched the model exactly. Okay, so now we have hydrogen and we have heat that is released in a predictable amount. And so how do we generate electricity and this clean water that I started off talking about? And so to generate electricity, what we do is we simply react aluminum and water in an enclosed pressure vessel, and that evolves hydrogen and steam. We then simply condense out the steam, separate it using gravity, and then we throw the hydrogen in through a catalytic converter, which removes the remaining oxygen that might have been dissolved in that water. And then that hydrogen, that pure hydrogen, goes into a fuel cell to generate electricity. And this is a 3 kilowatt power supply that we developed recently that was meant to replace a similar sized diesel generator. In particular, the 3 kilowatt tactical quiet generator that the Marines use for these types of rescue applications. We've demonstrated this same technology on a range of scales in the years since, ranging from a 50-watt personal power system that has a small fuel cell that can attach to just a simple canteen to charge your personal electronic devices. And then we've actually built a system that can be fully integrated into a BMW i3 electric vehicle. And that's a 10 kilowatt system, and this BMW can actually just drive around using aluminum fuel only. Essentially what we did here is we just ripped out the range extender and plugged in a fuel cell that runs the same reaction. Now we can also generate clean water using the thermal energy that's output. So here's a system that we developed where you just dump the aluminum fuel and some water in an enclosed cylinder that contains some seawater. And as that reaction occurs, we develop high pressures which can push that seawater through a semi-permeable membrane to separate water out via reverse osmosis. And then in this type of system, the hydrogen is simply a working fluid, and it's not consumed in this process, so we can then use that hydrogen to generate electricity later in a fuel cell. This plot here shows the amount of aluminum required per liter of seawater desalinated, 3.5% salinity seawater, as a function of recovery ratio. That's how much water we extract from how much water we put in there initially. It's because it's a batch process. And these curves represent the upper and lower bounds of that system depending on how well insulated you can keep that piston. And we show that blown up here is the lower bound, and we show that for low recovery ratios, we're hovering around 5 grams of aluminum per liter desalinated. 5 grams of aluminum is less than half of a empty soda can's worth of aluminum. Very small amount. We can compare this type of system to just simply boiling off the water by defining a standard performance ratio, which is just the ratio of the latent heat of the water that we've desalinated to the amount of thermal energy we've put into that system by the change in enthalpy from the product to the reactants of that aluminum water reaction. And show that in the upper bound case, we have a performance ratio of 40 for low recovery ratios, which means that we can desalinate 40 times more water than just simply boiling off the water in one stage alone. And to give you a sense for the state-of-the-art multi-effect distillation systems and multi-stage flash systems, which continuously recycle the latent heat of the water that you evaporate, those only achieve performance ratios in the range of 8 to 12. And so this has the potential to do much better than even those state-of-the-art thermal desalination systems. So wherever you might have access to scrap aluminum and you need water and you have access to salt water, this might actually be a good process to do not only for disaster relief, but also for large-scale desalination as well. And again, that depends on how much aluminum you have available. So to sort of paint you the total picture of what I'm trying to explain here is that after a natural disaster, scrap aluminum would be collected and processed into this fuel and then stored. You probably wouldn't do it right after a natural disaster. You'd probably wait till the initial aid efforts are completed, and you'd sort of operate one natural disaster behind. And then when the next natural disaster hits, this fuel could be distributed and then consumed to provide electricity and potable water. And what I've alluded to earlier is that this aluminum oxyhydroxide byproduct is actually quite valuable, and it can be sold for about $1 per kilogram. And compare that to the 50 cents per kilogram cost of the initial aluminum itself. And so you can sell this byproduct and potentially offset the operating costs of this type of system. So just really quickly, a couple key takeaways here. The climate has already changed, and we need technologies not just for mitigation, but we need technologies for adaptation to this post-climate change world, this Anthropocene, if you will. And aluminum scrap can actually be consumed in this new world to produce electricity and potable water locally. And a lot of places that simultaneously need fresh water and electricity also have issues with waste management and currently do not recycle aluminum. It ends up in the ocean, ends up in the trash. And so you can solve these two problems potentially simultaneously. And so I would then also encourage all of you to begin thinking of other ways we can convert things that are considered waste or trash to valuable resources locally. So that's all I have. Open the floor for any questions.
Two questions.
Yeah.
Do you have any, like, given that it's 50 cents per kilogram, like what the levelized cost of electricity or levelized cost of heat for cooking with this method might be?
I can show you a quick. We've done some basic economics analysis. So this shows in light gray here the cost of aluminum scrap in these different regions of the world. And in black is actually the amount of money you make by doing this process, by selling electricity and water at basically utility prices. The electricity would be sold at effectively net metering prices, so it's sort of a lower bound for what you can make. So you can make several times more than you would from just selling the scrap aluminum initially.
And then
Cost of the equipment,
Yeah, we haven't done that detailed of like a capital expense cost. But the idea is that you would actually integrate this into existing recycling plants to reduce a lot of that capital costs. And as I mentioned, the main capital cost initially would be the gallium and indium, but the operating costs are low because you can continually recycle that gallium and indium.
And then generally scrap aluminum has like lining of plastic and everything. So do you have any idea of putting it through this process, what kind of byproducts might result and what impact that would have on the user?
Yeah, so that's actually something we're looking at right now. We know that we can actually make fuel from soda cans directly already, but we haven't looked into what other compounds are being produced. Yep.
Thanks, Peter. That was a great talk. What's the shelf life once the fuel is activated?
So the fuel degrades in humidity, and so as long as you keep it away from humidity and you store it with a desiccant, it'll actually last almost indefinitely. And we can also store it in an inert oil, like mineral oil, and that also improves the shelf life. But we've had fuel sitting around for years that you can start up no problem.
Are there any concerns about premature oxidation or accidental oxidation and like having a violent reaction if you have too much stockpiled? Or
So if the only way that the aluminum could exist would be if you introduce water into wherever it's being stored. But you saw conveniently that if you keep it in a container that can vent the pressure, the natural tendency is for this to boil off all the extra water. So the reaction stops pretty quickly if you just let it go.
Last question. What do you see as the biggest issues with recycling the gallium and indium? Like, is it like technology issues? Is it the price?
Yeah. So the technology is actually being developed because gallium is a byproduct of aluminum smelting to begin with. It's naturally found where bauxite is found, and so people are already working on ways of extracting gallium from what's called the Bayer process for dissolving that bauxite ore. So there's a lot of people working on this. So it's just a matter of implementing it at this small scale. Currently, it's just being done at large scale.